points for using orbit illustrations.
I know, right? Fine. Thank you, guys. Go ahead.
All right, aloha everyone. I'm Celeste Jonganalen, and this is my partner Jason Gumbaugh. And today we are presenting our project entitled "Is the Moon Made Out of Cheese?" A spectroscopic analysis of the Apollo 11 and 16 sites.
So we would like to introduce you guys with two terms. One is Ameria, that is the dark Maria, the dark area of the moon. And we have the highlands, which is the brighter side of the moon, area of the moon. And for our purpose, we want to understand the geological history of the moon. Is the varying brightness on the moon due to internal processes or external processes, such as asteroids, solar winds?
So, for our hypothesis, we actually wanted to test something that is a little bit older. From the 1960s, it was generally accepted that the brightness of the moon is affected by grain size, not composition. And so, as you can see, this was an actual worry. This is the Apollo 11, and they have these foot pads because they were worried when they landed on the Maria, the dark area, that it would actually sink like quicksand. And so, as you can see, this is what they thought. We actually have an alternate hypothesis as well, which is that there will be some composition differences, and so we'll be looking for brightness changes, slope differences, and characteristic mineral absorptions. So for the method, we use hyperspectral images from the Chandrayaan mission, which is an Indian mission that orbited the moon from about 2008 to 2009, and this mission collected 83 wavelengths of data between about 0.5 to 3 nanometers. And so for the purpose of our project, we are using data from the Apollo 11 site as well as the Apollo 16 landing site. As you can see here, this is the Apollo 16, which is the Highland area, and the Apollo 11 was in the Maria. For the method, we actually selected 3 points in each of the landing sites, the actual Apollo landing site, as well as a bright spot and dark spot. And we did this so that we could actually see the amount of variance within each of the landing sites. Variance in brightness, by the way. So anyways, for the method, we used Myra AL software to perform statistical analysis. And when we were doing this, we selected 3x3 and 9x9 pixel sections. And the reason why we did this is so that we could define which pixel block would be the most appropriate for the rest of our analysis. And so as you can see over here, the black trend line is a perfect 1-to-1 ratio. So that would mean that the 3x3 and the 9x9 have no difference in standard deviation values. And so over here, the Apollo 11, it's much more spread out. And you can see that the 3x3 is actually lower standard deviation values than the 9x9. And this is actually pretty interesting because 9x9, you have more pixels, so you would expect a lower standard deviation value. And so what we suspect is that in the 9x9 pixel, there was 2 different compositions, measurement of different compositions. And so basically, that would cause the 9x9 to actually be less accurate than the 3x3. And in the Apollo 16, as you can see, it's pretty close to a 1-by-1 ratio, so they're pretty much the same standard deviation values to the 3x3 and 9x9. And so for the purpose of this project, we decided to use the 3x3 data analysis for the rest of our analysis, which I'll tell you about.
Okay, so for our method, we are analyzing the 3x3 data of the Apollo landing sites. We are essentially comparing the spectra. 3 categories: brightness, slope, continuum, and characteristic absorption. So this graph is based off laboratory results of olivine and plagioclase. As you can see, to the y-axis is reflectance. It is the amount of light reflected off the surface of an object. And on the bottom, the x-axis is wavelength, measured in nanometers. At about 500 nanometers, you can see that plagioclase is brighter than olivine. Olivine is darker. Next slide, please. And now we have our slope and continuum. The slope is also named as a continuum, just so that you guys know. So to determine the slope, we pick a point from the visible spectrum, located from 400 to 700 nanometers, and a point near the IR. So the black lines represent the slope of each graph, and as you can see in the plagial place, the slope of this graph is pretty flat. While in olivine, it's really positive and steep. So these differing slopes basically identifies the different composition in these minerals. So right here, oh, I found it, okay. Using that continuum, we can define the band center and band depth of each of these minerals. And for comparison, the plagioclase has a smaller absorption at a longer wavelength. Okay, so this is a plagioclase, right? As you can see, this is a longer wavelength, and the absorption is small. While the olivine has a deep band depth, see that red line right there? And the center lying around 1,000 nanometers. Okay, now time for our results. The spectra of Apollo 16 seems to be way brighter than Apollo 11. Apollo 11 is darker, as you can see. Now, for their slopes, you can see that Apollo 16 has a steeper slope than Apollo 11. And we can find the continuum removal by dividing the relative reflectance over the continuum slope. And I will explain to you why we would do that in the next slide. Okay, so we want to take out the continuum from the slope so we could better see the absorption dip of each spectrum. Now right here, this isn't really favorable data because you can see that there is jaggedness. That is caused by something we would call noise in the data. So the continuum remove plot, this is the one. Apollo 11, the center is around 1,000 nanometers, and Apollo 16, the center is around 2,000 nanometers. Now what we can tell is that the different band centers are caused by different minerals, therefore we can say that their composition is different.
So in conclusion, our results show that the Maria and the highlands differ in composition. Thereby, the hypothesis that grain size controls brightness of the moon's surface is false. From these results, we can infer that the moon's surface, change in brightness of the surface is due to internal processes rather than external processes. We would like to give a special thanks to Dr. Jeff Gillis-Davis, our wonderful mentor. Thank you so much for your time and effort. We'd also like to thank Dr. Matthews, Dr. Armstrong, and Mr. Nasser for putting on the High Star program. You guys are amazing. And Michaela Wandel for being an incredible counselor. Super fun as well. Love those trivias. And then Auntie Mary in the back. This program would not be possible if she didn't start it, and we're forever grateful. And all of our wonderful friends, you guys bring joy in the crazy data nonsense. Like, you know, if we're having a stressed out time, you crack a joke and we feel better. So thank you all. And do you have any questions?
Yeah, we'll take a few questions. Yeah, Esther.
Okay, so I was very interested when you talked about doing your sampling in terms of the 3x3 and 9x9 pixels, okay? And your hypothesis about whether there would be more variation in that. So I have two questions related to that. One is, do you know what physical size or angular size corresponded to one pixel element? Am I talking about things like rock shape, small grains, or something more extensive?
That's a very interesting.
Okay, so why we don't have that information right now is because we're using spectroscopy. We're just using wait, what? I'm sorry.
No, go ahead.
We
Please
would
forgive
be
us.
able to find that information. We just
actually, Jeff is right there. Jeff, do you know the meters per
Okay.
pixel?
Okay,
Hundreds of meters per pixel.
because that physically sets in your mind what kind of things could vary over that scale. Okay, right? And the second thing, my second question is, because you're using the same pixel size in two different missions, did that actually correspond to the same dimension in the imaging data of Apollo 11 and Apollo 16? So it's the same mission.
Yeah, it's not the actual
Yeah, so
Apollo
they use
mission,
the same-
it's one that went to go look at the different sites.
Oh, that's right. So
Yeah.
so that was standardized, so we know that.
Yes.
Okay, great. Thank you.
Thank you. Any more questions?
No, all right. So there is a typo. I'll just clarify that just fast. So this is micrometers. Micrometers. Okay, so the later graphs are correct, right? In the later graphs, the values are hundreds and thousands of nanometers. Okay, so these are correct.
Any more questions?
Yeah.
Why did you only show the respective wavelength range for the yellow and the blue data? If you only showed the interesting part and not the non-interesting part.
Just go with would that be these graphs here, where it's just the interesting part?
You should never ignore the other side.
Go ahead.
My answer to your question is that I accidentally failed my mentor and deleted the. I'm sorry.
Extra points for honesty and recovery.
Okay.
Points Gryffindor.
Actually, I think we have one more question from our students.
Oh, hold on.
Yeah.
No, why are you asking?
Oh, right there. Oh my goodness. We have a question, guys. Okay.
Okay, that was very spontaneous. Yeah, go ahead.
Okay, so while kind of analyzing, looking at the data for Apollo 11 and 16, so what actually causes the jaggedness of the data?
That is a very great question. I'll make this quick and easy. So the reason for the jagged look for the spectra is because of the noise from the data. The major noise in this in this case would be the temperature of the camera. The CCD, otherwise known as the Charge Coupled Device camera, were expected to be cold, but due to the orientation of the spacecraft in the camera outside, the camera was outside its designed thermal regime, which means that it was hotter and it couldn't really calculate it as well as the other data that we just saw.